Causal inference is a critical research topic across many domains. Therefore, various causal effect estimation methods for observational data have sprung up. Here, I will provide a comprehensive review of causal inference methods and the potential outcome framework. I will divide these methods into the following categories: reweighting methods, matching methods, tree-based methods, and others, including like stratification, multitask, meta-learning methods, and so on. Now let's firstly go to the reweighting methods. Due to the existence of confounders, the covariate distributions of the treated group and control group are different. This leads to the selection bias challenge. Simple reweighting is an effective approach to overcome the selection bias. We can assign appropriate weight to each unit in the observational data. Then a pseudo population can be created, on which the distributions of the treated group and control group are similar. Now, I can give you an intuitive example. Suppose that the age is confounder. There are two types of people, young people and older people. The young people have a 75% chance of receiving treatment, while the older people have only a 25% chance. If there are 4 people in each group, 4 people for young people and for older people, then we would expect that 3 of the young people receive the treatment and only 1 older people receive the treatment. We can see in the treatment group, we have more young people, but in the control group, we have more older people. In addition, age is a confounder, also have influence on the treatment effect. For example, young people always have better effect of treatment than older people for this medication. If we want to directly estimate the causal effect, for example, the difference in the average outcome between the first and second row, we will have bias. For the reweighting method, we could assign a weight of 3 to the older people in the treatment group and younger people in the control group. Then we will have the same distribution for age in the treated and control group. Then we can calculate the treatment effects. In simple reweighting methods, a key concept is that weight. It is also called balancing score, which is a function of X satisfying the treatment assignment W is independent of covariates given the balancing score. Among the balancing scores, one representative balancing score is the propensity score. The propensity score is defined as the conditional probability of treatment given observed variables. Based on the propensity score, we have the inverse propensity weighting, always called IPW, which assigns a weight to each unit based on their own propensity score. For example, it is in the treatment group, the weight is 1 over propensity score. If it is in the control group, the weight is 1 over 1 minus propensity score. Based on this reweighting, we can easily get the IPW estimator of APE. Both large and small sample theory have shown that the adjustment for the propensity score is enough to remove the bias due to all observed covariates. However, in practice, the correctness of the IPW estimator highly relies on the correctness of the propensity score. If there is slightly misspecification of the propensity scores, it will cause ATE estimation error dramatically. To handle this difficulty of estimating the propensity score, doubly robust estimator is proposed. It is also called augmented IPW. DR estimator combines the propensity score weighting with the outcome regression, so that even if one of the propensity score or outcome regression is incorrect, the estimator is still robust. It also can work. From the first equation, we can find the doubly robust estimator is composed of two parts, traditional IPW and the augmented part. In the augmented part, the M1X and M0X are the estimated treatment and control outcomes from the regression model. The theory can prove the DR estimator is consistent and asymptotically unbiased. If either the propensity score is correct or the regression model is correct, the DR estimator still can work, is robust. An alternative way to improve the estimation of propensity score is CBPS, covariate balancing propensity score. In the traditional IPW estimator, propensity score serves as both the probability of being treated and the covariate balancing score. In CBPS, it is proposed to employ such dual characteristics. CBPS estimates propensity scores by solving the following problem. In this formula, where tutor xi is a predefined function of xi, by solving the above problem, CBPS directly constructs the covariate balancing score from the estimated parametric propensity score, which increases the robustness to the misspecification of the propensity score model. Now let's go to another popular method, matching methods. As mentioned previously, missing counterfactuals and confounder bias are the two major challenges in the treatment effect estimation. Matching-based approaches provide a way to estimate the counterfactual and at the same time reduce the estimation bias brought by the confounders. As the formula in this slide, the goal of matching is for every treated unit or control unit to find one unit in the opposite group with similar characteristics. The matched sample can mimic an RCT. One can directly compare outcomes between the treated and control group within this matched sample. Here, the most important thing is how to find the matched unit or the neighbors. What distance metric should we use to compare the closeness between units? We summarize them into two categories. One is based on their original data space, like Euclidean space and Mahalanobis distance. Also, rich information is retained in the original covariate space, but it will face the curse of dimensionality. Theoretical studies revealed that the bias of matching methods increases with the dimensionality of the covariate space. Another category is transformed feature space, such as propensity score matching. Propensity score matching combats the curse of dimensionality. However, a one-dimensional propensity score space will lose most of the information in the data. Therefore, for now, they have developed a lot of other transformed feature space. For example, transform the treatment and control group into a balancing space, or utilizing the observed outcome information. Here, I give one example for propensity score matching. Propensity score denotes conditional probability of assignment to a particular treatment, giving a vector of observed covariates. Based on propensity scores, the distance between two units is the absolute of the difference for their own propensity scores. Later, the linear propensity score-based distance metric is also proposed. This improved version is recommended because it can effectively reduce the bias. After defining the similarity metric, the next step is to find the neighbors. Existing matching algorithms are divided into 4 essential approaches, including the nearest neighbor matching, caliber, stratification, and kernel. The most straightforward matching estimator is nearest neighbor matching, always called NNM. In particular, a unit in the control group is chosen as the matching pattern for treated units, so that they are closest based on this defined distance, like propensity or Euclidean distance. The NNM has several variants, like with replacement and without replacement. And according to the number of matched control units, we have one-to-one matching or one-to-multiple matching. NNM may have back matches if the closest partner is still far away. So we can set a tolerance level on the maximum propensity score distance to avoid this problem. This tolerance level is called caliber. The stratification matching is to partition the common spot like of the propensity score into a set of intervals. Calculate the impact within each interval. This method is also known as interval matching, blocking, and or subclassification. Kernel matching uses weighted averages of observations in the control group to create a new counterfactual outcome for treatment group. Therefore, one major advantage of this approach is the lower variance, because we use more information to create this counterfactual outcome. For the variable selection, to satisfy the assumption, the strong ignorability assumption, many literatures suggest including as many variables as possible. Of course, those variables are related to the treatment, assignment, and outcome. However, post-treatment variables, which are the variables affected by the treatment assignment, should be excluded in the matching procedure. Moreover, researchers also suggest excluding the instrumental variables and other irrelevant variables because they tend to amplify the bias of treatment effect estimate. Here is a summary of matching methods. We have discussed them before. Now let's look at tree-based methods. Tree-based method is based on decision tree learning, which is one of the predictive modeling approaches. Decision tree is a non-parametric supervised learning method used for like classification and regression. The goal is to create a model that predicts the value of a target variable by learning simple decision rules inferred from data. When the target variable is discrete, it is called the classification trees. The prediction error is measured based on its classification cost. In these tree structures, leaves always represent class labels, and the branches represent conjunctions of features that lead to those class labels. When the target variable is continuous, it is called regression trees. The prediction error is measured by the squared difference between the observed and predicted values. The term classification and regression tree, CART, is an umbrella term used to refer to classification trees and regression trees. In CART model, the data space is partitioned and a simple prediction model for each partition space is fitted. And therefore, every partitioning can be represented graphically as a decision tree. Now let's look at these two equations for estimating treatment effects. Mu Wx represents the mean outcome of the subgroup of units that fall in that specific node. Here we will have leaf-specific effect. It is the difference of the average treated outcome and control outcome in that leaf node. At that specific leaf node, for treated and control groups, they are balanced. In CART, a tree is built up until a splitting tolerance is reached. There is only one tree, and it is grown and pruned as needed. However, BART is an ensemble of trees, so it is more comparable to random forests. Like the plots in this slide, we can combine these two trees together. It will have more accurate splitting. BART is a non-parametric Bayesian regression model. Every tree in BART model is a weak linear, and it is constrained by a regularization prior. Information can be extracted from the posterior by a Bayesian backfitting MCMC algorithm. How can we use BART to estimate the treatment effect? BART is designed to estimate a model for outcome Y. The input is treatment assignment and covariates. Let T denote the binary tree, like the figure at the bottom. This is T. And M is the set of mean responses, mu I, for every leaf node. As CART, mu represents the mean response of the subgroup of units that fall in that node. In this figure, M is a set of 6 means associated with the 6 bottom nodes. Each TI/MI denotes a single subtree node. Given the tree model Tm and the treatment Z and variables X, we can define G of Zx Tm as the value obtained by dropping observation down the tree until it hits a bottom node. Finally, sum all of subtree models. We can estimate the Y as this formula. Now look at causal forest. Because a single tree is noisy, it is not always clear what the best causal tree is. This is the advantage of a forest over a single tree. Forest can be considered as nearest neighbor methods with an adaptive neighborhood metric. Tree-based methods seek to find training examples that are close to a point X. But now closeness is defined with respect to a decision tree. And the closest points to X are those that fall in the same leaf as X. Because the causal forest estimator can be thought of as an adaptive nearest neighbor method, where the data determine which dimensions are most important to consider in selecting nearest neighbors. Such adaptivity seems essential for modern large-scale applications with many features. And it allows for data-driven feature selection, and at the same time maintaining the benefits of classical methods, like asymptotically normal and unbiased point estimates with valid confidence intervals. In addition, it is very easy to extend to multiple treatments. Next, we can briefly introduce some other methods like stratification, multitask, and meta-learning methods. First one is stratification. Stratification adjusts the selection bias by splitting the entire group into subgroups, where within each subgroup, the treated group and control group are similar under some measurements. It is also called as subclassification or blocking method. Like the plot at the bottom, one population is divided into 5 subgroups based on their own colors. Each one subgroup is one block. In each block, they have similar characteristics. Here is color. Now we have the block-specific effect. We can get the difference of the average treated outcome and control outcome in that block. Therefore, the ATE is estimated as the following formula. Weighted sum the difference of the average treated outcome and control outcome in every block. Here is the multitask learning method. Because the treated and control group always share some common features, but at some time they also have their own characteristics. Therefore, causal inference can be conceptualized as a multitask method. These shared layers for treated group and control group together, but they also have their own specific layers for treated group and control group separate. Above methods control the confounders and estimate the treatment effect simultaneously. Meta-learning algorithms separate them into 2 steps. This is the difference. There are 2 procedures. The first one is estimate the conditional mean outcome, and the prediction model learned in this step is the base learner. Step 2 is to derive the CAT estimator based on the difference of results obtained from step 1. Recently, there are several meta-learning methods like T-learner, S-learner, X-learner, U-learner, and so on. If you are interested in them, you can find the details in our survey paper.